Have you ever wondered how Minecraft renders voxels? I have, and I have spent countless hours coming up with my own way of rendering voxels. But what is a voxel? To understand a voxel, we first need to start with a quad. A quad is just a simple 2D square defined by 4 points in space, but we make it 2 triangles so that the GPU can understand it. Now, take 6 of these quads, arrange them into a box, and you have a voxel that the GPU can understand. But storing voxels individually for an infinite world is inefficient, so we group them into manageable chunks. In my engine, the world is divided into 32 by 32 by 32 chunks. But how do we store data inside a chunk? The easy answer is a 3D array. But if we flatten it into a single 1D array, we get a more cache-friendly solution. The index can then be decoded into a relative 3D position, which can easily be encoded back into the index. I take this a step further by using Morton code, a clever way of ordering the array so that blocks that are close to each other in 3D space are also close to each other in our 1D array. So, what about all the different block types? How can we efficiently store them? The answer is by using compression algorithms. The two compression contenders for voxel data is run length encryption and palette compression. Run length encryption combines similar data next to each other in an array. With palette compression, on the other hand, we create a block palette, which allows us to use smaller data types like 8-bit numbers to represent blocks, since most of the time we can assume every chunk doesn't contain more than a few different block types. And if it does, we just use a slightly bigger data type. I use palette compression because usually we only have to store voxels within a render distance, so memory usage really won't be a problem, and for chunks further away, we can archive them and store them to the disk using even stronger compression. Okay, we have covered how to store the data on the CPU, but on the GPU, we only want to provide the data we need to render voxels. I use 2 buffers. Buffer 1 is like a directory holding metadata for each chunk. Buffer 2 contains the actual block data per chunk, where each voxel uses 2 integers. Integer 1 has the relative block position encoded into the integer, and integer 2 has a neighbor bit mask for the 26 neighbors around the voxel. Buffer 2 does not contain air or blocks that are completely surrounded. So, how do we render it all? The traditional approach is by building memory-hungry vertex meshes of all the block faces, but as I've already revealed, I already store all my block data in 2 buffers and not vertex meshes. Instead, I use a powerful and modern rendering pipeline called mesh shaders, but it is not that easy. Not all GPUs support mesh shaders, including my GPU. Luckily, all of our data are same-sized cubes, so we can kind of replicate mesh shaders as close as possible by using compute shaders and indirect instance rendering. So how does this work? A GPU compute shader scans buffer 1 and adds rendering commands to a command buffer where each block is its own instance, and every instance exists out of enough vertices to represent a cube. We then let the GPU handle the command buffer and render it. This raises a few questions on how we handle culling and effects, like backface culling, inside face culling, and ambient occlusion, since most of these are traditionally done by taking advantage of building a vertex mesh from a chunk on the CPU. First, for backface culling, we only ever see 3 faces of a cube, so we make our block instance 3 quads. The vertex shader then figures out which face we are working with per vertex. Next, for inside face culling, we use the determined face and check if its neighbor is visible from the neighbor's bit mask. That same neighbor mask gives us a beautiful and cheap solution for ambient occlusion. The shader checks 3 neighbors around each corner of a block face to determine 1 of 4 darkness states voxel corners can be in. Per voxel optimizations are mostly easy, but large-scale optimizations are what makes or breaks performance. The first large-scale optimization is frustum culling, which is trivial. The compute shader can simply ignore any chunk that's outside the camera's view. To possibly push performance even further, I experimented with aligning chunk data sizes to powers of 2 and sorting the chunks by chunk data sizes. I then use a parallel scan algorithm to compact the rendering list caused by excluding chunks from the rendering list. The hope is to improve cache coherency, but I have not benchmarked this properly. Currently, I am working on rendering very simplified chunk meshes so that I can obtain an approximate depth map for as cheap as possible for the purpose of occlusion culling. So, what's next? My main focus right now is perfecting the score pipeline, which will include stuff like occlusion culling LODs and many more. I hope you enjoyed and thanks for watching.